Alrighty, here are the solutions. Make sure you go through them only after you've taken on the problems on your own. Pretty straightforward here. The definition of a radian angle measure, the number of radius lengths in the arc length of the angle. And of course it does not matter the size of the circle you use. We can use any size because the radius is always the same proportion of the circumference. The circumference is 2 pi r, so there are always 2 pi radius lengths in a circle. And so that allows us to always measure an angle in terms of radians, regardless of the size of the circle we use. These should all be pretty straightforward. The two that I'm going to discuss quickly, at 5 pi over 4, the cosine of 5 pi over 4 and the sine of 5 pi over 4 are equal. So that's why I've written it as such. 17 pi over 2 is in the same place as pi over 2, and that means the tangent there is undefined because it's a vertical terminal side. And at negative pi, we see that that's where the tangent is a horizontal line, the slope of a horizontal line, and so that's going to be 0. Okay, this problem is a little bit tricky. So 1 radian is going to be a little short of pi over 3. Remember, pi is a little bit greater than 3, so you can approximate. So 1 radian will be here, 2 radians will be here. Now remember, we're looking for the greatest value of tangent, and tangent is the slope of the terminal side. So basically we're going to compare the slopes of these terminal sides. This is a positive slope, and once we enter the second quadrant, we see negative slopes. So both of these, 2 radians and 3 radians, are out of the question. What about 4 radians though? 4 radians certainly gives you a positive slope. And we can approximate, we can say, look, 4 radians is a little bit short of 4 pi over 3, because 4 times something a little greater than 3 divided by 3 is going to be about 4. The tricky part is, how do we know whether this slope is greater than or less than this slope? Well, it's pretty easy, and let me explain why. Basically, what we want to know is whether this terminal side is closer to 4 pi over 3 than this terminal side is to pi over 3. So we need to know, what is pi over 3 approximately, and what is 4 pi over 3 approximately? Well, 4 pi over 3 is approximately 4.1887, which means that 4 radians is about 0.1887 units away from 4 pi over 3. So this distance here is 0.1887. Pi over 3 is about 1.047. So 1 radian is just 0.047 units away from pi over 3. So clearly this 1 radian measure is much closer to pi over 3 than is 4 radians. And so this is going to be slightly more shallow than this is, and therefore the tangent of 1 is going to be greater. So tangent of 1 is the greatest value. And you can check that if you go onto Wolfram Alpha or type in your calculator tangent of 1 and tangent of 4, you will see that tangent of 1 is a little bit bigger. This slope is a little bit steeper than this slope. Sketching the graph of cosine and sine, I'm just going to pull up my unit circle and use it to plot some points here. So I'll start with cosine. Cosine of 0 is 1. Then I'm going to go over to pi here. Cosine of pi is negative 1. Halfway in between at pi over 2, cosine is 0. So I'm plotting these points here. Cosine of 2 pi is again 1, and halfway in between I'm at 3 pi over 2, and cosine there is 0. And then I can continue that pattern on past 2 pi, and to the left here, if you move clockwise around your unit circle, you'll see moving pi units gets you to negative 1, a cosine of negative 1, and halfway in between, cosine will be 0. Simply connecting with a smooth curve. Sine of x, obviously very similar. Sine of 0 is 0. Sine of pi is also 0, and halfway in between, at pi over 2, the value of sine is 1. Then at 2 pi, sine is again 0, and halfway in between, at 3 pi over 2, sine is at negative 1. We can then continue that pattern past 2 pi, and moving clockwise, we know that the sine of negative pi is going to be 0, and halfway in between, that's at 3 pi over 2, the sine is negative 1. And so then we connect with a smooth curve. So here is the donut problem. We've actually gone over the solution before, but I'm going to go over it again in case you've forgotten. So the interior of the donut is a circle, so is the exterior. The interior circle has a radius of 1 inch, hint hint, unit circle, and the exterior has a radius of 4.2. So Jason, I'm going to annotate what Jason does in green, and I'm going to annotate what Russell does in purple. And the annotation is what's key to figuring out how to mathematically determine who eats more of the donut. So let's start with Jason. He's going to travel around the interior of the circle. So what he does, he starts at point P, and he travels 2.5 inches around the inside of the arc. So to make this as accurate as possible, notice that the inside, right, has a radius of 1. So if you think of this length being 1 inch, maybe that gets you here, 2 gets you here, 2.5 maybe gets you somewhere around here. All right, so he travels this arc length in green. That's 2.5. All right, then it says that Jason extends lines from the center of the donut through his starting and ending points all the way to the exterior of the donut. So from the center through his starting point to the exterior, and from the center through his ending point to the exterior. Okay, so now we see what Jason does, and now let's take a look at what Russell does. He starts at the point Q and measures 10 inches around. Now, let's label this correctly, right? So this is radius of 1. Now, the radius of the exterior, this length here, is 4.2. I'm going to label that in purple. So if this is 4.2, then maybe this is one radius length, another of these radius 4.2s, and maybe it gets a little further out here. Let's just, for the sake of the problem, say that he goes a little past where Jason ends up. So this arc length here in purple is the amount that Russell travels, and that is 10 inches. Then he does something very similar. He starts at the center and draws a line through his ending point and through his starting point. So then it says that both are going to eat the portion of the donut that is around the arc and between the two lines. So for Jason, around the arc and between his two lines is this much of the donut. For Russell, around his arc and between his two lines is going to be this much of the donut. So according to the way that we've drawn it, it's pretty obvious that Russell would be eating more of the donut. But we just drew this diagram, and we don't know if we're being exactly precise, right? We don't know if this 10-inch arc actually gets us further than this 2.5-inch arc on the inside. So we want to think about what would cause one portion to be greater than the other. And we can see pretty clearly here that it depends on who creates the bigger angle, right? According to the way we've drawn it, it's very obvious that Jason has drawn a slightly smaller angle, whereas Russell's angle is a little bigger. So we have to think about, how do we measure an angle? Well, we use radians, and radians is nothing more than the number of radius lengths in the arc that you create. So Jason very easily creates an angle of 2.5 radians because his radius for his circle is 1 inch. So there are 2.5 1-inch radiuses in 2.5 inches, right? 2.5 divided by 1. Now, to determine the angle that Russell creates, we need to know how many of these 4.2-inch radius lengths are in the 10-inch arc. That's begging for us to do a little bit of division. So to figure out the angle that Russell creates, we'll take the arc length of 10 inches and divide it by the radius length of 4.2 inches. Doing so tells us that the angle that Russell creates is 2.38 radians. So Jason actually is the one that creates the bigger angle, and therefore he's going to eat more of the donut. What is cool about this problem is it emphasizes how it does not matter the size of the circle that you use, that a radian angle measure is dependent on the radius length. And since the radius length is always the same proportion of the circumference, 2 pi r units, we are able to use any circle that we want. And so using the unit circle is obviously much easier, right? Because 2.5 divided by 1 is 2.5. It's very easy for us to compute. And it also allows us to think about some things in real life that aren't exactly unit circles, such as the exterior of this donut. There is one other way to do this problem, which is to think about if you extended what Jason does out to the exterior of the circle, what arc length would he create? And the way to do this is to notice that you start with something that's 1 inch and you turn it into a radius of 4.2 inches. You're multiplying by 4.2. So you would multiply your arc length by 4.2 as well, and you get 10.5, which is obviously a little bit bigger than 10. So if you were to extend this radius of one circle out to a radius of 4.2, the arc length of 2.5 would be an arc length of 10.5. But I like this way a little bit better.